Welcome back to The Explainer. Today, we're diving straight into Episode 4, High Trust Crossings, where autonomous systems must stop. We're going to take a serious architectural look at a problem that is, honestly, quietly keeping platform leaders up at night, and that's the critical limits of autonomous agents. You know, we're moving way beyond the hype of AI coding assistants here. We need to talk about the strict operational realities of governed machine execution. I mean, think about it. What actually happens when an autonomous system hits a boundary it simply isn't allowed to cross? Let's get into it. Okay, let's kick things off with a concept that kind of fundamentally rewires how we think about AI engineering. Autonomy is not the absence of control. It is the result of sufficient control. This quote hits the nail on the head because it brilliantly dismantles the prevailing industry myth. The ultimate goal of a governed system is definitely not maximum unbounded autonomy, where an agent can just do whatever it wants. No way. That's a total security nightmare. True defensible autonomy actually only exists because the controls around it are absolute. So, here's our structural blueprint for today. First, the autonomy myth, then defining high trust crossings, followed by low risk versus high trust. After that, we'll cover enforcing explicit execution authority, then governance, defense, sustained autonomy, and finally, when infrastructure itself fails. This is a rigorous, logically sequenced briefing tailored right for architects and security leaders. Right, starting with part 1, the autonomy myth. Let's challenge the idea that unchecked AI agents are safe just because their models are super smart. The absolutely crucial point to understand here is this: an agent's intelligence does not equal its authority. We often kind of confuse a highly capable language model with a highly trusted operator, but they're entirely different beasts. A model might be incredibly brilliant at writing a complex database migration, sure, but that brilliance doesn't magically manufacture its own right to act on it. Unbounded execution, meaning an agent writing, testing, and deploying all without explicit external human authority, is an uncontained blast radius. It's simply an unacceptable operational risk. Moving on to Section 2, defining high trust crossings. If unbounded execution is too dangerous, where exactly do we draw the line? Well, here's the exact definition. A high trust crossing is a transition boundary where the consequence, authority, reversibility, or data sensitivity of an execution materially changes. So why does this matter so much for your architecture? Because look, autonomy is incredibly useful, but really only when it's kept safely inside a bounded operating envelope. The second a system needs to cross from, say, a sandbox into a production environment, or touch protected data, or execute an irreversible, destructive action, boom, that's a high-trust crossing. The rules must immediately change. Which brings us to Section 3, low risk versus high trust. Let's really contrast what this looks like in practice. Notice the clear contrast between these two worlds. On one hand, we have low-risk meshwork. This is fluid execution, right? Kind of like water flowing smoothly. It's your read-only observation, drafting a pull request, or just ordinary isolated repository work. The system can be highly autonomous here. But then, on the other hand, we have high-trust crossings. Things like rotating a secret, mutating a privileged API, or accessing protected internal evidence. These are definitely not fluid. They're like giant bank vault doors. They require explicit, hard stop and go logic. To manage all this, GhostMesh routes work through canonical execution classes. Notice how the logic breaks down here? If a task requires consequential judgment, it demands human authority. If it's just an exact supported operation, you use a direct connector. For known transformations, like building or testing or deploying, you use a deterministic adapter. You actually only use a model-backed delta for tasks that require genuinely novel reasoning. The whole point is that GhostMesh is designed to route work through the least expensive, most deterministic surface possible. You definitely don't want to spin up a highly permissive, expensive AI model just to ping a simple API. Let's jump to Section 4. Enforcing explicit execution authority. How do we actually build those heavy bank vault doors? To cross a high trust boundary in GhostMesh, you need strictly layered trust zones. This means requiring explicit execution authorities, things like an explicit worker identity, not just some shared generic token. You need exact head association, meaning the authority is tied directly to a specific immutable commit, not a moving branch. You also need temporary writer leases, immutable receipts, strict scope limits, and above all, fail-closed behavior. And let me be clear, these aren't just nice-to-have best practices. They are absolute constitutional requirements of the mesh. So let's walk through these mechanics in action during a governed crossing. Step 1, claims and leases are required to completely prevent collisions. Step 2, the exact head association is locked. If the underlying code changes even a tiny bit, the authority is instantly voided. Step 3, deployment admission is rigorously checked against policy. And step 4, immutable evidence, basically a receipt, is generated. The worker proves it completed the exact job it was authorized to do, leaving a completely durable trace. And this perfectly illustrates the ultimate safety net: fail closed. An ambiguous worker absolutely cannot silently inherit authority. In the GhostMesh source material, there's actually a really fascinating real-world example where the architecture intentionally halted a model-backed execution route. Why did it do that? Because a required API credential was intentionally missing. Instead of just falling back to a generic cloud identity or guessing its way forward, the system threw a hard stop. Missing credentials or unresolved paths must always fail closed. Observe how identities are handled during what GhostMesh calls the skills high-trust second crossing. They use two completely separate credentials. First, an isolated writer credential with temporary write access scoped purely to that exact job. Second, an independent observer credential, which is a totally distinct read-only identity. Why is this so crucial? Because a worker can never, ever be allowed to certify its own mutation. The observer verifies the writer. You literally never let a student grade their own test, right? Let's trace the exact life cycle of that temporary authority. It kicks off with a signed admission event, moves into bounded task execution, and then, this is critical, explicit temporary credential revocation. And they don't just revoke it and cross their fingers. The architecture requires a post-revocation HTTP 401 proof to practically guarantee the token is dead before the lease and budget are finally released. Cleanup and explicit revocation are mandatory architectural controls here, folks, not just optional housekeeping. Now, moving into Section 5, governance defends sustained autonomy. We often view governance as a bottleneck, but that's totally backward here. Consider this paradigm shift. Autonomy is not a permanent permission. It is a sequence of temporary, typed, evidence-bearing capabilities. You see, governance isn't a brake on the system. It's the engine that actually makes sustained autonomy defensible. Without these guardrails, the very first time your agent makes a catastrophic error, leadership will shut the entire program down in a heartbeat. Governance is literally what allows you to keep running. When we stack the two approaches side by side, the differences are just stark. Under unbounded autonomy, your blast radius is super high, traceability is totally opaque, and reversibility is basically unknown. You're just hoping for the best. But under governed bounded autonomy, the blast radius is strictly contained. Traceability is guaranteed through those immutable receipts we talked about. Reversibility is tied to exact rollback identities. By bounding the operating envelope, GhostMesh prevents silent corruption and ensures that when failures do happen, they are visible, typed, and fully recoverable. Finally, Section 6, when infrastructure itself fails. What happens when you build the perfect mesh, but the ground beneath it just gives way? To ground this explainer in stark operational reality, we have to look at the August 6th GitHub outage that was detailed in the GhostMesh architecture notes. Actions and pages were throttled, workflows just stalled out, queued jobs failed. Everything we just talked about relies entirely on infrastructure, and suddenly the provider itself became a live failure domain. This really exposed a massive provider concentration risk. That massive incident forced a huge architectural realization. No execution provider may be the canonical representation of an executable GhostMesh operation. Because think about it, if your entire autonomous mesh dies just because one cloud provider goes down, you don't actually own your system. This incident heavily drove the GhostMesh doctrine towards sovereign, independent operation. The architecture simply has to be provider neutral. So this raises a really uncomfortable question for platform leaders. What happens when infrastructure fails, even after your high-trust boundaries are perfectly designed? You can have the absolute best claims, leases, and identity separation in the world, but if your runner can't reach the API, the whole system just halts. Here's the truth. A completely governed architecture can still encounter outages, partial failures, stale state, failed runners, or broken dependencies. The real test of an autonomous system isn't just how it operates when all the lights are green, it's whether the system can recover seamlessly without losing the truth of its state. If your cloud provider vanishes tomorrow, does your mesh survive or does it burn down with the infrastructure? That perfectly sets the stage for our next explainer when the mesh fails. Thanks so much for joining me, and I'll catch you in the next one.